Hi y'all, today's data structure is graphs. So some of you guys have seen graphs in classes like Math 55 and so forth. Hi y'all, today's data structure is graphs. So some of you guys have seen graphs in classes like Math 55 and so forth, or CS 70 maybe. What's a graph? Usually we give a graph a name, call it G. A graph is a set of vertices, which are sometimes also called nodes, and a set of edges that connect them together. And the edges are sometimes called arcs. So these are like the edges in a tree. And in fact, a tree is a particular, well, an unrooted tree is a particular kind of graph. But graphs in general, often mathematicians like to use the notation G equals VE, by which they mean that a graph is an ordered pair consisting of a set of vertices and a set of edges. Now, this notation looks deep, but it really isn't. It's just formalism. Some people just love formalism. The reason why you might find a notation like this useful sometimes is it's handy when you want to, say, have two different graphs that have the same set of edges. Like, for instance, on Friday, we'll talk about the spanning tree of a graph, or spanning trees of a graph, where you might have another graph called T, which is a spanning tree, and maybe its vertices are V and its edges are F. And so this notation is a way of just representing the fact that this graph and this graph have the same vertices, which is handy sometimes. Now, graphs come in two types. There are directed graphs, and there are undirected graphs. In a directed graph, or a digraph for short, every edge E is directed from some vertex V to some other vertex called W. And so typically the way we draw it is like this. We'll draw little circles for each node, call those V and W. And a directed edge will look like this. And usually, of course, the arrowhead tells you where it's directed to. Now, we have a notation for this, which is we say that E is itself an ordered pair. Just like a graph is an ordered pair, well, so is an edge. It's an ordered pair giving the vertex that you point away from first and the vertex that you point to. And the vertex that you're pointing away from is called the origin of the edge. And the vertex that you're pointing at is called the destination of the edge. So an undirected graph is a lot like a directed graph, except that E is an unordered pair. What do I mean by that? Well, if I say that an edge is an unordered pair, well, we still write it VW, but now the order does not matter. Or in other words, if you have an unordered pair VW, that is exactly the same thing as the unordered pair WV, but only in an undirected graph. In a directed graph, they're different. So the way you draw this in an undirected graph is like this. You just leave out the arrowhead. Question? Called a what? aware of any name specifically for undirected graphs that's shorter than undirected graph. Most of the graphs that people use are undirected, so I think they're more common than directed graphs. If people just say graph, you usually assume it's undirected until someone says digraph. Other questions? Okay. All right, so there's lots of different applications for graphs. One is you could use it to model a street map. So to give you an example, here's a directed graph, first of all. Now, in this graph, for this particular graph, I'm using the vertices to indicate intersections between streets, and the arrows to give a block's length worth of street that connects one intersection to another intersection. And since there are a lot of one-way streets around, I've used the directions of the directed graph to indicate which direction you're allowed to drive. And so just to make this a little bit more recognizable, here are some street names. So that's an example of a directed graph, and there the reason you have the directions, as I said, is so you know which way you're allowed to drive. An example where it makes sense to use an undirected graph, and there's just no reason to have a directed graph, is in what's called an adjacency graph that tells you which things adjoin each other. So I can draw a city adjacency graph that tells me which Bay Area cities share some border and which ones don't. So there's your other example. So coming back to graphs, a graph is a set of edges. And in this set, you're not allowed to have two copies of the same thing. So it shouldn't surprise you that multiple copies of an edge are forbidden in either kind of graph. But in a directed graph, you can have both VW and WV. Those are different edges. So for instance, Bowditch is a two-way street. And so I use two different directed arrows to indicate that. In an undirected graph, VW and WV are the same edge, so you can only have one of it. You can also have self-edges. So a self-edge is an edge of the form VV. And I didn't use any self-edges in these graphs up here because for the particular applications, a self-edge just doesn't really mean anything. But if you want to have self-edges, usually they're drawn either like this in a directed graph or just like this in an undirected graph. And for some applications, that's useful. Sparse matrices that come up in linear algebra is an example where you often have self-edges, which refers to the numbers on the diagonal of your matrix. If you don't understand what that means, don't worry about it. It's for people who know linear algebra. Most things that you would want to use graphs for involve paths through the graph from one node to another. So a path is a sequence of vertices wherein each adjacent pair in the path are connected by an edge. Now, if the graph is directed, then the path has to align with the directions of the arrows. You can't follow one arrow pointing forward, another one pointing backwards in a path. You have to have them all pointing forward. Now, the length of a path is the number of edges in the path. Just like in a tree. But again, let me remind you, it's not the number of vertices, it's the number of edges, which is one less than the number of vertices. So if you have, for instance, in that graph over there, 4, 5, 6, 3 is a path. And it's a path of length 3. And just like I mentioned with trees, it's perfectly respectable to talk about a path of length 0. So if I just write 2, the path that starts at intersection 2 and ends at intersection 2 and doesn't go anywhere in the meantime, that's a path of length 0. Now, the distance from one vertex to another is the length of the shortest path from the first vertex to the second one. So, a question? Absolutely. There can even be a path 4, 5, 2, 1, 4, 5, 6, 3, 2, 1, 4, 5. This is a perfectly respectable path, too. So a path can revisit a vertex any number of times, reuse an edge any number of times, do a joyride around the city. Yes? Absolutely. If there are self-edges in the graph, then a path can include self-edges, yes. Other questions? So a graph is said to be strongly connected if there's a path from every vertex to every other vertex, or now, in undirected paths, this is usually just called connected. The reason why in a directed graph they add this extra word, strongly connected, is just to remind you that there has to be paths in both directions. So it's not enough to just have a path going from U to V. There also has to be a path going back from V to U if a graph is going to be considered strongly connected. More definitions. The degree of a vertex is the number of edges incident on that vertex. Now, self-edges count as 1, not 2. And I realize that in Math 55, they either do or at least used to teach this differently, where they said that self-edges count as 2 in order to make the counting in some theorem work out. But in CS 61b, we're going to use a different definition. Self-edges count as adding 1 to the degree of a vertex and only 1. In a directed graph, you can talk, oh, question? Well, in directed graph, we usually count separately the in degree and the out degree instead of talking about the degree. Yeah, so they add 1 to the in degree and they add 1 to the out degree in a directed graph. That's right. Other questions before I go on? Okay, to punctuate what I was just saying, in a directed graph, we have in degree and out degree. So the in degree of a vertex is the number of edges directed toward the vertex. And the out degree, obviously, is the number directed away. And as we just discussed, yeah, so if you have a self-edge in a directed graph, then that adds one to the in degree and adds one to the out degree. So just to have a few more examples, in this graph, for instance, Berkeley has a degree of 4, Piedmont has a degree of 1, and intersection 6 has an in degree of 2 and an out degree of 1. All right, so that's the basics about graphs. And so there's all kinds of things you can imagine doing with graphs, like figuring out whether there's a route that will get you from this intersection to that intersection, and if so, what's the route that takes the fewest blocks, for instance. And so we'll look at algorithms that solve those and other questions. Yeah, question here. Mm-hmm. Yeah, the length of the shortest path. That's right. Before we can build algorithms, though, we need a data structure to represent graphs. So let's look at graph representations. So there are two that are really popular and that you see all the time. One of them is called an adjacency matrix. The other one is called an adjacency list. The adjacency matrix is the simpler one of the two. It really is pretty much just a matrix. So you take a two-dimensional array whose height and width are the number of vertices. So this notation, v between absolute value signs, this is a notation that means the number of elements in the set v, in which for this set means the number of vertices. So you have a number of vertices by number of vertices matrix of Booleans. And so here's an example of the adjacency matrix for this graph. I will number the rows. I will number the columns. And then I put trues in any column where there's a directed edge going from the thing on the left, the number on the left-hand side to the number on the top. So there's an arrow from intersection 2 to intersection 1. So I put a true in that spot in the matrix. And so those are all the trues. Everything else is false. For the city graph, you can do something similar, except I'm not going to draw the whole thing because I think part of it will get the point across. So again, you fill this in with trues for anything that's connected together. Though you'll notice one thing about this matrix is that because it's an undirected graph, the adjacency matrix is symmetric. which means that entry ij is always the same as entry ji. And if you want to, you could economize on the size of your adjacency matrix a little bit in the undirected case by only saving the lower diagonal, or the lower triangle, of the matrix. So if you want, all you really have to save is this part here, and you can figure out the other parts by reflecting below the diagonal. So are there any questions about the adjacency matrix representation? Yeah. Oh, for the directed graph, the arrow goes from this stuff to this stuff. So this, for instance, would mean it goes from 2 to 1. Other questions? So looking at the digraph, it should be clear that the maximum possible edges that you could have in a digraph is v squared. That's for a digraph. For an undirected graph, it's approximately half of that, because for an undirected graph, the maximum number of edges you can have is the number that fits in this staircase here, which is slightly more than v squared over 2. But the point is, the number of edges can be quadratic in the number of vertices in either case. And so that adds up to a lot of storage space. You know, if v is big, if you have a huge number of vertices, that adds up to a lot of storage space. And sometimes the number of edges that you're actually storing is far less than what is in the number that you need to store in an adjacency matrix. There are a lot of graphs that only have, say, a linear number of edges in the number of vertices. For instance, these graphs here are both what are called planar graphs. A planar graph is a graph that you can draw on the blackboard without any edges crossing. And it's well known, I won't prove it, it's actually hard to prove, but it's well known that planar graphs have a linear number of edges. So for an awful lot of the types of graphs you would want to store, the amount of storage space you're going to take up with an adjacency matrix is way more than the number of edges you actually want to store, and that's pretty wasteful. And a graph is generally called sparse if it has far fewer edges than the maximum possible number, v squared or whatever. Now you'll notice my definition of sparse graph is not really formal. It's a colloquial definition. And the word sparse does not really have a strict mathematical meaning. People just use sparse to talk about graphs that have a lot of zeros in the adjacency matrix. And so usually when people talk about a sparse graph, they're talking about a graph that has asymptotically fewer than v squared edges, but that's not always true. Sometimes they're just talking about a graph that has maybe only 1 in 10 edges. So for every t you have in the adjacency matrix, maybe you have 9 falses. And even in that case, you can still save memory by using a different representation. And so that's where the adjacency list representation comes in, is how to encode these graphs in a more compact way when we're not using a lot of edges. So adjacency lists work like this. An adjacency list is actually a collection of linked lists. Each vertex in the graph has its own linked list. of all the edges that go out from that vertex. Or to be more precise, all the edges that have V as their origin. And so for our intersection graph up there, it'll look like this. And we can do the same thing for an undirected graph, and now every edge gets entered twice. So for instance, the edge connecting Albany to Kensington will be in both Albany's list and in Kensington's list. So hopefully you get the point. Any questions about that? Yeah. That's right. So there's one arrow going from 3 to 2, and there's another one going from 3 to 6. What about the x? That's how I draw a null pointer. So this x just means there's no more destinations in the list. Oh, because I forgot it. Other question? So the first nice thing about the adjacency list is it doesn't use v squared memory. The amount of memory used, and I hope it's clear why, is proportional to the number of vertices plus the number of edges. So there's no v squared term anymore, unless e is v squared. But if e is small, like if it's a planar graph, for instance, then this will be a lot better, take up a lot less space than an adjacency matrix. But of course, it's a more complicated data structure. There's more overhead for chasing pointers. It's slower to look things up in it because you have to walk through a list. So there's advantages and disadvantages. Now, a few details about getting this data structure to work out. If your vertices are just represented by consecutive integers, then it's easy to do it. You just use an array. So there you have an array of lists. But in a lot of real-world applications, you're not necessarily going to be given a list of consecutive numbers and told these are your vertices. Instead, you might be given strings like Albany, Emeryville, Berkeley, and some application will just pass you a string, and somehow you have to figure out what list is associated with that string, and you don't have a number, or a nice handy compact number at any rate, associated with that string. So how do you look up the list for Berkeley or for Kensington? Well, that's what hash tables were made for. And you can use a hash table for virtually anything. You can use it to map strings to their adjacency lists, or any object. Basically, any data structure you can dream up, you can use as a vertex in a graph. and then just use a hash table to map it to its adjacency list. And so there the idea is just every entry in the hash table is going to have a key, which is the vertex name, say Albany, and an associated value, which is the list. And you use the key to look up the value. And so that's how you do an adjacency list. So, any questions on that? So as I was saying, there's a trade-off. If you have a really sparse graph, the adjacency list makes sense. It's a lot more space and time efficient. But if you have a graph that's not very sparse at all, say you have the complete graph, then it's a lot less efficient. A complete graph is a graph that has every single edge it could possibly have. Every vertex is connected to every other vertex. But even if you don't have a completely complete graph, even if you just have most of the edges, then an adjacency list is still pretty inefficient compared to an adjacency matrix because the constants are bigger. I mean, they both take v squared space to store a complete graph, but with the adjacency list, you have all these list nodes you got to store, you've got all these pointers you got to follow. You have to walk through the list to find anything instead of just looking something up in an array really fast. And so if you have a complete graph, you don't want to use an adjacency list. There's just no point. Any questions on that? Yeah? Oh, well, I would still use a hash table. So the question is, suppose that I wanted to use the adjacency matrix representation, but I had strings as my values. So they're not numbers. I can't just look them up. Well, in that case, what I would do is I would use a hash table that creates a map of strings to integers. So that way I could just go through my strings and assign them all numbers. I could say, all right, Albany is 1. Kensington's 2, Berkeley's 3, Emeryville's 4. And then whenever someone gives me a string, Berkeley, I can look it up in my hash table and see, oh, Berkeley's number 4. And then once I know the number, then I can look it up in the adjacency matrix. So, good question. Yeah? I don't understand. Why does a collision mess you up? Oh, no. I mean, we're using a traditional hash table where, you have a table and you use chaining, and each string gets assigned a different number, no matter what. And the way you resolve collisions is the same way you always resolve collisions, which is you actually store all the entries. You actually store all the entries in a chain, and if you have a collision, you're going to still get the right answer because you're actually going to test the value. You're going to say, if you're looking up Albany, you're going to test, is Albany equal to this string? No, it's not. Is Albany equal to this string? Yes, it is. So that's number 1. And then you use the number 1 to look into the adjacency matrix. So is that clear? Okay. Yeah. Well, you need to do whatever you did in homework 6 or 7, whichever the hash table homework was. I mean, you could literally take your homework and just use it to map strings to numbers, and then once you've got those numbers out, then you use that for the adjacency matrix. So graphs have traversals just like trees do. And so a graph traversal is an algorithm that visits each vertex once. And we're going to learn two in this class. One is called depth-first search. Which, since depth-first search is a long name, we will usually abbreviate to DFS. And the other one is called breadth-first search. Or BFS. And the way these traversals work is that depth-first search basically tries to search the graph as deeply as possible, as early as possible. Breadth-first search, what it does is it starts at some node, and whatever node you start at, then it visits that node, and then it visits all the nodes that are one node away from that node, then it visits all the nodes that are two nodes away from that node, and then all the ones that are three nodes away, and so forth. So if you do depth-first search on a graph that represents a tree, it will do a pre-order tree traversal. If you do breadth-first search on a graph that represents a tree, it'll do a level-order tree traversal. So in order to do these graph traversals, you want to make sure that you never visit the same node twice. And in a tree, that was easy, because there's only one path to get to any given node in a tree. But in a graph, there's many different ways you might be able to get from one node to another node. And so you want to make sure that you don't visit a node repeatedly. And so each vertex is going to have a Boolean field called visited. Could someone in the back go close that door, please? Thank you. That tells us if we visited the vertex before. And so whenever we're thinking of visiting a vertex, we check if we visited before, and if we have, we don't visit it again. Yeah? At what point do they get reset to unvisited? Basically, you need to write a separate loop that goes through all the vertices and resets them to unvisited. If you want to go through them again, then every time you'd want to do that, you have to reset all of the vertices to unvisited. But you have an array of vertices, generally, or some representation of all the vertices in your vertex set. So you just go through that set, you set everything to unvisited, and then you do your graph traversal. So let's assume for now that we have a graph that's strongly connected. When depth-first search visits a vertex V, it checks every edge out of that vertex in order, and when it finds a vertex that it has not visited yet, it recursively visits it. So here's the code. So the method is called DFS. We call it on a vertex u. We visit that vertex. We set the visited field to true so that we won't visit it again. Then we look at every edge going out of the vertex u and find all the other vertices that it could lead to. And for each of those vertices, we check if they're visited, and if they've not been visited before, we recursively visit them. This visit routine can do some arbitrary computation, like add up the populations of all the cities in our city graph. And so let's go through how depth-first search will work on our intersection graph. Suppose that I start depth-first search at intersection 1. Then I'm going to have a stack for my DFS calls. And the bottom level DFS call is going to have u equal to 1. So then I visit 1. 1 is visited. I look at all the edges out of 1. There's only 1, and that's 4. So 4 goes on the stack. I visit 4. I look at all the edges out of 4. There's only 1. It goes to 5. I visit 5. There are 2 edges out of 5, so I'll take them in order. First, I'm going to visit 2. So I visit 2. I look at all the edges out of 2. There's 1 edge that goes out of 2, but it goes to a node that's already been visited. So I backtrack. I'm done with that. There are no more edges out of 2. I backtrack out of 2. Are there any more edges out of 5? Yeah, there's 1 going to 6. So now I put 6 on the stack, and I visit 6. Are there edges going out of 6? Yeah, there's 1 going to 3. So now 3 goes on the stack. I visit 3. I look at edges out of 3. Well, this one's already been visited. This one's already been visited. Everything's been visited, so I'm done. And the running time of this if you use an adjacency list, then it runs in v plus e time, because it has to check every edge once. But if you use an adjacency matrix, then it runs in v squared time. Because that's how long it takes just to check every edge in the adjacency matrix to see if it exists or not. And you have to do that to find all of the edges going out of each vertex. Questions? All right, on Friday I will cover breadth-first search.